In 1927, an English scientist named Hermann Arthur Jahn, along with a Hungarian physicist, Edward Teller, proposed this Jahn-Teller effect. According to this effect, any nonlinear molecular system which has degenerate electronic configuration is considered to be unstable. In order to gain stability, it will undergo distortion in its geometry to get stabilized. To understand degeneracy, let us consider an octahedral complex of Cu2+, which is bounded with 6L- ligands. Due to the interaction of ligands, the outermost electronic configuration of copper 2+, as we all know, it is 3d9. Due to the interaction, the d orbitals get splitted into two sets. The triply degenerate set, which contains dxy, dyz and dzx orbitals, and the Eg orbitals contains dz square, dx square minus y square orbitals. The electrons in T2g orbitals are completely filled, but in the Eg orbitals we could see there are two electrons in dz square and only one electron in dx square minus y square orbital. Since there are two electrons in dz square orbital, there develops a repulsive force between these two electrons. Hence, the electron from dz square orbital gets shifted to dx square minus y square orbital. This phenomenon of a metal atom having two different electronic arrangement of same energy level orbitals is known as degeneracy. That is, when the electron is present in dz square orbital, the electron density is higher in this orbital than dx square minus y square orbital, which causes higher screening effect of the positive charges of Cu2+. As a result, while the ligand approaches towards the z-axis, it will be lessly attracted by the copper 2+ ion, since the electrons are fully filled. But in the case of x and y axes, they have a vacant space through which they can accommodate an electron. The attraction will be higher in x and y direction than in the z direction. As a result, the ligand along the z direction will move away from the central metal ion, whereas the ligand along the x and y direction will come closer to the metal atom. This type of distortion is known as Z-out distortion. This distortion causes a change in the bond length. For example, in complex CuF2 the bond length along x and y axis reveals that it is 1.93 Armstrong unit, whereas the bond length along the z-axis is 2.27 Armstrong unit. The bond length along z-axis is higher than the xy directions. This is the consequence of Z-out distortion. As the ligand present along the z direction moves away from the central metal atom, the axis along the z direction is elongated. Due to this, the electrostatic repulsion experienced by d electrons of the metal ion from the negative charges of the ligands along the z direction becomes less than the similar repulsion experienced by the electrons along the x and y direction. Due to this, the dz square orbital will be of lower value, that is, it is reduced by half delta naught, and dx square minus y square orbital will be of higher energy, that the value will be increased by half delta naught. In case 2, that is, the ninth electron of copper 2 plus ion is present in the dx square minus y square orbital. The electron density will be higher along the x and y direction than the z direction. As a result, the negative charges of the ligand along the xy direction will be less attracted by the nuclear charges of Cu2 plus ions than the negative charges along the z direction. Since there is a vacant space in the z orbit, the ligand which approaches towards the z direction will be easily attracted. Since the copper ligand attraction along x and y direction are less, the ligand which approaches in these directions will move away from the central metal atom, which will cause a larger bond length along x and y direction. Since the ligand along z-axis comes closer to the central metal atom, the bond length will be low in the case of z direction. Such type of, in toto, it gives a compressed tetrahedral structure. This type of distortion is known as Zn distortion. Since the metal ligand bonds along the x and y direction gets elongated, the electrostatic repulsion between the d electrons of the metal ion and the negative charges of ligand will be along xy direction will be less compared to z direction. Hence, the energy of dx square minus y square orbital is lowered, and the energy of dz square orbital will be of higher energy level. In certain octahedral complexes, such as a complex which has d0 electronic configuration, which do not contain electrons in both T2G set and EG set. In D3 configuration, there are 3 electrons, one each in triply degenerate orbitals. In D5, there are 3 electrons. Since it is a high spin complex, one each electrons are present in each triply degenerate orbitals, and 2 other electrons are present in each EG orbitals. In these cases, since the electrons are uniformly distributed, in certain cases they are half filled or completely filled, which favors stability. As a result, electronic complexes with these type of electronic configurations will not undergo Jahn-Teller dissociation. In certain octahedral complexes, such as a complex which has D0 electronic configuration, asymmetric T2G orbitals, that is an uneven distribution of electrons in T2G set and EG set, whereas consider an example configuration of D5, there are three electronic configuration, one each in triply degenerate orbitals. Here in D5 there are three electrons. Since it is a high spin complex, X orbits one each electrons are present in each triply degenerate orbitals, and two other electrons are present in only one electron each EG orbitals. EG set is symmetrically filled. Since the electrons are uniformly distributed, equal number of certain cases they are half filled or completely consider an example of which favors basic electronic configuration. As a result of Fe2 plus electronic in which complexes with these type of electronic configurations contains only two electrons, not undergo one electron Jahn-Teller dissociation in certain octahedral complexes, another electron in D such as square orbit. A complex which has D0 electronic configuration, the dissociation will be it less do not contains electrons in both T2G set and EG set. The orientation of orbitals configuration of there are T2G electrons will be one each in between the axes triply degenerate orbitals. As a result, in D5, the ligand while approaching the central high spin complex will undergo one each electrons are present in each, whereas in triply degenerate orbitals, orbital is considered and two other electrons the are orientation of electron will be on the axis. EG orbitals. That will cause in these cases repulsion or since the electrons are uniformly distributed, but in certain cases they are half filled or completely filled. The electronic orientation will be in between the axes. As a result, so it will electronic disturb the geometry with these type of electronic configurations will not undergo Jahn-Teller in such type of in certain octahedral complexes such as apart from complex which has D0 electronic configuration there are another which do not contain electrons which come under Jahn-Teller dissociation T2G set and EG set static Jahn-Teller dissociation and dynamic configuration dissociation. There are in three static Jahn-Teller dissociation, one each in occurs in degenerate orbitals, which have in D5 unevenly there are three electrons distributed since it is a high spin configuration. In each one each electrons are present in each. It is a permanent degenerate orbitals, and does not two other electrons are present. Changes or influenced by temperature. Each EG orbitals. In these cases, while the dynamic electrons are uniformly distributed, it is in a temporary cases effect. They are half filled or completely filled. The bond which favors stability. The geometry as a result is electronic to be disordered complexes, but at higher temperature, these type of electronic configurations will not undergo Jahn-Teller dissociation. In certain octahedral complexes, this dynamic Jahn-Teller dissociation complex which has D0 electronic configuration at low temperature, which do not contains electrons at the outset. We have learned that EG set the Jahn-Teller effect in D3 was proposed configuration to remove the degeneracy there in a non-linear complexes. One each in degeneracy will occur in complex in D5. The electrons are asymmetrically filled since it is unevenly distributed. How the degeneracies are present in each either by elongation or compression of the geometry. Two other electrons the degeneracy is removed, and this elongation or compression is being detected by since the electrons are uniformly distributed and electronic spectroscopic in certain cases techniques. They are half filled or completely at the end. We learned about stability, static and dynamic Jahn-Teller dissociation, electronic where the static Jahn-Teller dissociation electronic configurations in will not undergo it is a permanent Jahn dissociation.
In
Whereas
certain
dynamic
octahedral
Jahn
complexes,
dissociation is a
such
temporary
as
effect which
a
occurs
complex
only
which
at
has
low
d0
temperature. Electronic configuration which do not
I
contain
thank you all
electrons in both for your patient
T2G
listening
set
and EG set. Thank you. In